Okay, so in this video we want to go over the just general log functions. Right? So just general log functions. Okay, so we saw previously, right, when we had the general exponential functions, they either looked like this or like this, depending on what the base was, right? A to the x, a to the x. Now, in particular, what we want to notice is that these functions, they are one-to-one, right? Continuous one-to-one functions, which means that they have an inverse, right? And we are here to define that inverse, right? So here, if a is bigger than 0, and again, a not equal to 1, right? And again here, a bigger than 1, a less than 1, but bigger than 0. All right, and f of x is equal to a to x, then we want to define its inverse essentially. We want to define the logarithmic function. Function with base a. As log base a of x. So what we have is, so then what we have here, thus log base a of x is equal to some value y, if and only if, right, because of the nature of inverses, a to the y to be equal to x. Right, and in particular, log base e of x is what we've been calling the natural log of x. All right. And then just to a heads up here, I think just common notation here is in algebra books and really any lower division type math books. And when I mean lower, I mean at this level and below, right? Once we get to upper division courses in college and beyond, when we see this in textbooks, right, we're referring to this as log base 10 of x. As you see, if you get to any math forward, like any upper division math classes, when you see the log base a of x, they actually are referring to the log base e of x, right? And really this makes more sense if we think of, there really is only one log, that being the natural log, the log of base e, right? Log base 10 is really more because of our number system being a base 10, I think, which is why it's the standard in lower division books. But, you know, it can get quite confusing. But for our particular textbook that we're working with, and any kind of previous ones that you saw, when you just saw log, they're referring to log base 10. Right? Okay, so just kind of just wanted to mention that here. And again, our cancellation laws, like our inverse, the composition of an inverse and whatnot, a log base a of x is equal to x. And again, this works for a bigger than 0. And log base a to the x, that's equal to x. And this is x can be any real number. Okay, so now we see how, well, now we define this, right? This is just kind of something we set out as, you know, the subject of math. This is what a logarithm represents, right? So it all comes down to the natural logarithm. As we'll see in introducing the change of base formula, there really is only one log. The rest, as we'll see, is just a ratio of the natural log. So let's introduce the change of base formula. So what this states is that log base a of x is equal to the natural log of x over the natural log of a. All right, so here we want to prove this, right? So this is the change of base formula. So our proof here is we have y equals to log base a of x. So this is true, again, if and only if a to the y equals to x. All right, again, this all derives because of the nature of the one-to-one, the fact there's an inverse. This has to be true. So let's start here, right? Let's start by taking natural log of both sides. Natural log of ay equals to natural log of x. And using properties of natural logs, we get y natural log of a equals natural log of x. Or in other words, y is natural log of x over the natural log of a, but we see y is also equal to log base a of x to equal to natural log of x over natural log of a. All right. And that concludes the proof, right? And as we could see, any logarithm of any base can be boiled down to just a ratio of two natural logarithms. So that means that we now have a formula, or not yet, but we're going to derive the formula for the derivatives of a natural log of base a. Right, so that's our next step here. How do I do something like this? Okay, so I'll use the above formula here. So I'll use the formula, the change of base formula, right? Because, and the reason why I want to do that is, well, I know the derivative of the natural log. Remember, ln of a, just a constant, so I can just pull it out, right? Of this differential, this operator, derivative operator. Okay, and now we have something like this. Okay, and then taking the derivative of that is just 1 over x. So we get 1 over x ln of a, and that gives me the derivative of a natural log of base a. All right, makes sense, right? Since it's a ratio of logs, that ln of a just kind of comes along for the right. It's just a constant, and we're really just taking the derivative of the natural log. All right, so let's do a couple of examples here. So dx, a basic one, let's say we just had log base 7 of x, right? So think of it as derivative of natural log, which is 1 over x, and then the natural log of whatever the base is of this natural logarithm. And that's it, right? That's how we take the derivative here. Now for something a bit more involved, let's say we had dx log base 5 of x e to the x. Okay, so now let's say we had something like this. Okay, so this is going to require the chain rule. Again, one step at a time for the chain rule. All right, so derivative here is 1 over the inside function, which is x e to the x times the natural log of 5. That's our base. Okay, and now as we work our way multiplied by the derivative of the inner function, which is x times e to the x. So here we need a product rule. So product rule, take the derivative of the x, which is just 1. So we're left with 1 times e to the x. Plus, leave the x alone. Derivative of e to the x, which is just e to the x. All right, and then simplifying things here, I can see I can factor out an e to the x, and we're left with 1 plus x over x e to the x ln of 5. That reduces to 1, and we get 1 plus x over x times ln of 5. All right, and that is how we take the derivative. Now, in terms of, well, how do we integrate a log of base a? Well, we don't have the tools just yet, right? So here, just to make sure, I think it's always important if we know what we can and cannot integrate, because then at least that knows that we have some gaps in our knowledge, right? Not that they don't exist, the integrals, but we just don't have the tools for that right now, right? Because if we have log base a of x dx, right? My first thought would be, well, how can I write this as a natural log. And ln over a is just a constant, so I could even do this, ln of x dx, but I don't know how to do this yet, right? I know how to take the derivative of that, but the integral of that is something that I just don't have the tools yet. Okay, so we will develop them in the next chapter, chapter 8, where we go through all the different derivatives, all different types of integration techniques. But for now, just realize that this, right, as well as just the general or just the natural logarithm, we don't know how to find the integral just yet.